Okay, so now that we have actually talked about finding the inverse trig value, trig functions, antiderivatives and integrals, definite integrals, now's a good time to just step back and review for a second because we need to make a little bit of a differentiation between some of the types of expressions that we come across when we integrate. I'll point out some of these forms look really, really similar, right? These three integrals right here, a, b, and c, they all contain that same structure, that square root of x squared minus 1, with just a few differences in the way the expression is dealt with. So how should we deal with this? Well, okay, so we think about what forms we know. We might think immediately when we see that square root of x squared minus 1, aha, that is the one where we have arcsecant. And arcsecant is the form where we say if we take the antiderivative of du divided by u square root of u squared minus a squared, then we're set. And this is certainly going to be that kind of function right here, right? We can see that we've got x and x squared minus 1 under dx, and so the form exactly mirrors that situation, and so we should definitely see 1 over a times an arcsecant of u over a type of situation right here, right? But what's wrong with that here? Well, in this case, the problem is that we don't have x in the denominator, we have x in the numerator. So the difference between these two integrals is that, well, this one is certainly not, while it's similar, it is not an arcsecant function. As a matter of fact, this is the kind of one where we just have to use a direct substitution and let u equal our quantity under the radical here. This one would have to be x squared minus 1 because when we make our replacement, we're going to get du equaling 2x dx, and we certainly have an x dx in the numerator right here. So this is going to help us rewrite our integral in the form 1 half of du, right? Let's make this clear. We have 1 half du replacing x dx in this case, and that's going to be divided by the square root of u, which is an expression that we can rewrite using our exponent rule, our general exponent rule, and then take the integral there, right? So this one, not too bad, actually a little bit easier than the last one as long as we've got that x up there, but we do have to make a note of where these expressions are alike, right? Now, in this last case, we've got a little bit of a different issue because where there is no x in the numerator and there's no x in the denominator, and it's not exactly the same as the arc sine either, right? Arc sine would be the one where we have du over the square root of a squared minus u squared, and that order is important. So I'll tell you, in this particular case, we don't have the capacity yet to do that. We haven't studied anything. We have to do a little bit more advanced work before we can come back and deal with this kind of integral. So at this point, given our methods for inverse trigonometric functions, for our natural logarithm integrals, and substitution methods, we don't have the method to solve this. So for right now, we're going to have to leave this and not be able to evaluate it. Now we can say this about any kinds of these expressions right here, right? Here's another one. What does this have to do with our inverse trigonometric functions? Well, I would say that one thing that we need to be careful of is how do we deal with these kinds of integrals. Well, here we go again, right? This is the kind of expression we might think, well, what am I going to do with this ln x? So now, when you come across an expression that contains something like an ln x or an evx or something like that, it is important to recognize how do we evaluate these kind of things by thinking about the kind of substitutions we can make. And usually that means that we should identify something we can take a derivative of directly. Right here, in our first case in A, we might note, well, okay, I don't know what to do with natural log of x, but I do know that when I take a derivative of the natural log of x, I get 1 over x dx. And look at what we've got right now. We certainly have that situation, don't we? We have dx over x right here, and we have a u in the denominator, and so we've got something that looks more like this, du over u, which interestingly is going to become a natural log of the absolute value of u plus a constant. And look at what we substitute in for u, natural log of x. So this is really going to be more like the natural log of the absolute value of the natural log of x plus a constant. Ooh, that's sort of a weird one, but it fits. Well, how about this second one over here? The natural log of x dx over x. Well, we might notice that we can make the same sort of substitution again, right? This time, where we make u equal to the natural log of x, we get du, of course, still equal to dx over x, which we certainly have right here. And so we have an integral this time that's more like u du. And this is a power rule, not a log rule, so it's going to come out slightly differently. Even though they look really, really similar, we're going to end up with 1/2 u squared plus a constant. And u being the natural log of x means we're going to be taking 1/2 of the quantity natural log of x squared plus c, right? Notice that this square cannot come down and just be this x squared, right? It's natural log of x times natural log of x, so it's a slightly different answer. How about this last one? Well, once again, we're kind of stuck. I will tell you in advance the method we're going to need, and this is going to be addressed in a different video, is going to be integration by parts. What we call integration by parts, which is sort of a product rule for integrals. And we're going to do that in a future video. So for right now, we're going to leave this topic and come back later when we have a better idea of what it is we want to do with this one. So good luck with your integration problems.